Hi, welcome to TEC Tube. I am your host Ryan Hoger, and today we're going to explain the basics of a heat pump. What is a heat pump? What does it look like? How does it work? So let's go ahead and get started here. So I'm going to use some illustrations to kind of help us along. This is our first one that we're going to look at. So in order to understand a heat pump, you actually need to first understand what your air conditioner does. Your air conditioner does not make the air cold. I mean, it does, obviously, but don't think of it that way. Air conditioners don't make air cold. Air conditioners remove heat from the air. If you think of it that way, everything becomes very logical as far as the heat pump discussion goes. Let me get a little laser pointer out so we can kind of get driving here. So on the left over here, I got two examples here. This is like a residential house. On top is cooling. Outside is a condensing unit outside in someone's yard. Inside is an evaporator coil sitting in their fan coil or on top of their furnace or however you want to visualize it. So that evaporator coil's job in life is to absorb heat. He absorbs heat. That's him over here on this drawing. He absorbs heat in this coil. And then we take that heat. Sorry, right here, evaporator coil on the left side. We take that heat and we send it to the outdoor unit. Same thing happens here. Take that heat, send it to the outdoor unit. The outdoor unit, which has the condenser coil, his job is to reject heat. So evaporator coils absorb heat, condenser coils reject heat. They both have a fan on them, right? There's a fan on this coil, on the evaporator. There's a fan over here on the other coil. Both have coils, both have fans, right? So in the summertime, inside this house, it's say 75 degrees, and outside it's maybe 95 degrees, and I'm able to take heat from inside and shove it into the hot outdoor yard, kind of defying the laws of physics there. If you're not sure how that works, watch our refrigeration cycle video and we'll kind of explain that. When it comes to the heat pump side, it's the exact same thing, except I'm gonna take this evaporator coil that's in someone's house, and I'm gonna set it outside in their yard. And I'm gonna take the condenser coil, I'm gonna pick it up, and I'm gonna set it in their living room. Now I don't really wanna pick up those two coils and move them. So instead what we do is we add one more component to a regular standard AC system. It's called the reversing valve. That guy's job in life is to make this guy, the indoor coil, become the condenser coil, and make the outdoor coil become the evaporator coil. They're the same physical coils, they switch jobs in the winter. And the reversing valve is what allows that to happen. So instead of sending refrigerant from the compressor over to the condenser, now we send refrigerant from the compressor over to the evaporator coil. Just reverses the direction that everything goes. So now what's gonna happen is the evaporator coil sitting outside, and by the way, when we have a heat pump, we usually stop saying evaporator coil and condenser coil, and we just say indoor coil and outdoor coil. So the evaporator coil, the outdoor coil right now, he's going to absorb heat, use the refrigerant system to take it inside to the condenser coil where we can use the heat. So now it's a cold day outside, say 30 degrees. I'm going to grab whatever BTUs I can, whatever heat I can out of the 30-degree outdoor air and bring them over to my inside. And you say, wait, Ryan, how can I get heat from the cold outside and bring it to my already warm inside? Well, you were doing it in the summer. You had a quote-unquote cold inside, and you were taking the heat and shoving it to the hot 95-degree yard. So I can move heat from cold to hot with the refrigeration cycle. And that's what we're gonna do with the heat pump. Move heat from cold to hot. Make it warmer. Now, as it gets colder outside, there's less heat to get, and my amount of heat that I can get out of the heat pump gets less and less and less as the temperature drops. That temperature where I can no longer make enough heat is very, very dependent on the model and sizing of that heat pump. It could be 30 degrees outside, it could be 15, it could be 0, it could be -10. So there's a lot of different outdoor air temperatures that cutoff point may happen depending on how the system was selected and designed. Why do we want to do this? Why would you want this heat pump system? Well, for one, if you have a heat pump air conditioner, you don't need a gas furnace, and there's some advantages to that. Now, some places gas is super cheap. Like where I live, gas is super cheap. It's the most inexpensive way for me to heat my house, so I do that. In other places, that's not true. If gas prices are relatively high, or if somebody's quote-unquote stuck on propane, they don't have any other choice because they can't get natural gas and propane's expensive, or oil or whatever, it starts balancing out to go with the heat pump. A furnace, the best furnace on the market, the absolute best one you can go buy is 98-point-something% efficient. That means 2% of the energy coming from the gas company goes out your flue and gets wasted. Boiler, the same thing. Best boiler that I could find listed anywhere was 96% efficient as far as an AFUE goes. It means 4% of the energy is getting wasted out the flue, just gone. Electric heat is perfect. It's 100% efficient. Every kilowatt that comes down in your electrical wires from the power company gets turned into usable heat. It's perfectly efficient, right? Now, electric may cost more than gas, so you may choose to heat with gas. An air source heat pump, like I was describing to you right there a second ago, that guy is going to be, let's say, 300% efficient. I got a range on here because it depends on the outdoor air temperature. And of all the models we use residentially, the worst one is 210% efficient. The best one's 380%. That means for every dollar of electricity that I buy, I'm gonna get $2, $3, $4 worth of heat out of that guy. 2, 3, 400%. It's significantly more efficient. But wait, how can it be more than 100% efficient? Well, with a gas furnace or boiler or even electric heat, I'm buying a fuel and I'm converting that fuel into heat. With a heat pump, I don't do that. I am only buying electricity on a heat pump to move heat. I'm paying to move it, not paying to make it. I have to move it from outside to inside. I don't have to make it. Whereas gas furnace, boiler, electric heat, they're all making heat. An air source heat pump is just moving heat. That's why it can be so much more efficient. Water source heat pumps and geothermal, which I'll explain in a second, can be even more efficient than an air source heat pump. So what do these heat pumps look like? Well, for your residents, it looks like a regular air conditioner. If you walked by it, you wouldn't know it was an air conditioner or heat pump. You would have no way to tell, right? You have to kind of know what to look for. But visually, it looks exactly the same on the outside. On the inside, instead of a furnace, I got a device that looks exactly like a furnace, but there's no gas connection to it, right? There's just a coil and a fan, no gas burning section. Commercial systems, same kind of thing. Indoor and outdoor unit split system. I could also do a packaged rooftop where everything's built in one. I could do dual fuel systems where I have a gas furnace and a heat pump, both. I bought both. I got a little protection there. If gas prices go up or down, electric goes up or down, I can play the game on which one I want to use at any moment. And as the outdoor air temperature drops, I can turn off my heat pump and not even use electric heat either, and instead run my gas or propane furnace. Most ductless mini splits, they are also heat pumps. Even if you're buying it for cooling only, you're probably getting a heat pump version. They're almost all heat pumps at this point. You can also get multi-zone versions. We have 2, 3, 4 different indoor units all paired off of one outdoor unit, and he can send cold or hot refrigerant to either one of those guys. You can do a variable refrigerant flow system. It's more commercial orientated. Same kind of thing. I could have multiple outdoor units feeding a bunch of indoor units, 10, 20, 30 of these things. And I can send individual ones hot or cold refrigerant. He can get hot while he gets cold, while he shuts off, while he gets hot refrigerant. I can heat and cool rooms simultaneously. It ends up being very efficient to do that. And then the last category I mentioned is water source heat pumps. The traditional water source heat pump for your typical like downtown condo or downtown office building, that guy, instead of sending his heat to the outdoor air to get rejected for cooling, he sends it to a refrigerant loop. So he dumps his heat into a refrigerant line. Or in the heat pump mode, he takes his heat from a refrigerant line. So some of these indoor units in blue are in cooling mode. They are taking their heat from the space and dumping it onto a water piping system. The red ones are taking heat from the refrigerant or from the water loop and sending it to the refrigerant. So I still have the same components, indoor fan, outdoor fan, right? Which is gonna be way outside on the cooling tower. I have an indoor coil and outdoor coil. But instead of rejecting the heat to air, I'm rejecting it to water, and I'm using a pump to send the water to the outdoor coil, which is a cooling tower in this case. And I can have a geothermal loop, which is exactly the same thing as a water source heat pump, the exact same piece of equipment, except instead of sending my heat outside to a cooling tower to reject it to the air, I'm gonna send my heat down into the ground. I'm gonna reject it into the ground and warm up the ground. Take the heat from your building or house, warm up the ground. Or in the wintertime, I'll take it out of the ground and back into my building. And the more heat I send there in the summer, literally the more heat's available to me in the winter. It's like a giant battery, if you will, thermal battery. So all kinds of different flavors on the heat pump. The ones we're gonna see most are gonna be the air source residential split heat pumps. That's by far the most common. And if you need help figuring out whether it's cost effective or not, we have a whole series of videos for Carrier, Bryant, Heil, Day and Night, whatever, that tell you how to calculate the efficiency of a heat pump and when to use a gas furnace over a heat pump, etc. Hopefully that helps you guys out. Thanks for joining us.